Ah, c'est intéressant ça. Pourquoi ça avance pas? Ok, c'est pas grave. Ah non, c'est ici, c'est grave. Apparemment, mes slides n'avancent pas. Si, ça y est, c'est parti.
Ouais, ça y est, ça va.
Très bien. Donc en fait, je suis Bruno Sudret, je suis professeur à l'ETH Zürich. Et donc, dans mon groupe, on s'intéresse à la quantification d'incertitudes en général. Pour des problèmes qui vont de la fiabilité des structures, l'analyse de sensibilité, la calibration de modèles, l'optimisation sous contrainte probabiliste. Alors, comme vous le voyez, mes slides sont en anglais et j'ai beaucoup de mal à parler en français quand les slides sont en anglais. Donc, si ça, comme l'intervenant précédent a fait son exposé en anglais, je vais me permettre aussi de parler en anglais. So we will talk today about uncertainty quantification, more specifically about structural reliability analysis, and I will introduce surrogate models in this area, and more specifically Krigging or Gaussian processes. So we have seen this kind of scheme already many times this morning. I don't think I need to comment too much. We are interested in quantifying uncertainties into the results of a computational model where we have some information about the sources of uncertainty. In my case here, we use probabilistic modeling, not intervals, and the propagation of uncertainty gives us information about the output uncertainty or the model response uncertainty. Here, I will today talk more specifically about the so-called structural reliability problem, where in fact the output of our model, let's say y, should not be greater than a threshold. And the point here is to compute the probability of exceedance of this threshold, which in practice is supposed to be a probability of failure. So in practice, we very often have this kind of model or representation where the quantity of interest for this failure criterion is the response of a quite complex computational model, typically finite elements. The threshold is given by standard or by something that is relevant for the analysis. And so we typically define a limit state function, which for each parameter or each set of parameters in the input space tells us if the system would be safe or failed. And the standard notation is that the negative values of the limit state function corresponds to a failure domain. Then with this notation, the probability of failure is basically related to the probability that this G function is negative. And so in practice, it's formulated as a kind of complex integral over this implicit failure domain here, where the dimension of the integral is typically large. This is the number of parameters of the problem. And for industrial cases, very often we can have 10 to 50 to 100 parameters. And in the end, we also hope that the result is a small probability of failure because we want to have safe systems. So this makes this problem quite difficult. This is a long story of methods starting in the 70s from this approximation first, second order reliability method. In the 80s, 90s, there were many different simulation methods that have been developed, a combination of the two also. But the point is that even with simulation methods that are well designed and have nice properties, the computational cost remains very expensive, even with the one which I call here variance reduction methods, such as importance sampling or subset simulation or line sampling. So for addressing real industrial problems, there's no way but using so-called surrogate models which will replace the costly computational models. So in this presentation, I will talk about surrogate modeling in general, but more specifically about Krigging, which is one of the most used surrogate models in the context of structural reliability analysis. And then I will explain how we can use this Krigging model in a so-called active learning process to very efficiently compute probabilities of failure. So what is a surrogate model? Remember, I consider here as the previous talks, non-intrusive approaches. So my original finite element model here is just a mapping from input to parameters to output quantities, and it's supposed to be black box. I don't want to change the equation. I just want to be able to run the model. So a surrogate model will be an approximation of this computational model that I will build based on a very limited set of runs of the model. Here, these points here are selected in the input space. And then I assume certain shape for the surrogate model, which is related also to the regularity of the original model. So typically, here you have a list of very popular ones, from polynomial chaos expansions to Krigging and neural networks. All those models have a very clearly defined analytical expression. Here, for instance, that one is just a series of polynomials with certain unknown coefficients. And the goal of fitting a surrogate model is to fit the parameters in this column here based on the data that has been simulated. So it's a kind of data science problem at this point, except that here we have small data, because the whole point of having surrogate models is that we use a very limited number of runs of the true model. In the end, what we get is indeed this analytical expression, whatever the choice we made, and this is very, very fast to evaluate. That's the point. So generally, to build a surrogate, we start by defining this so-called experimental design. So points in the input space, typically covering the input space, such as Latin hypercube sampling techniques. And then we run, of course, the model for each of these points. And then with the data set that we have produced and a proper algorithm, learning algorithm, we will fit the parameter of the surrogate. So of course, depending on the type of surrogate, we will get different types of learning algorithms. In the end, what we get is an approximation of the true model, and the main point is the gain in terms of computation. So a typical finite element model for a realistic system, let's say, would cost an hour or few hours of calculations. A surrogate, typically you get 1 million of runs of this surrogate with your laptop. So for a single run, the difference in terms of computational cost can be 6, 7, 8 orders of magnitude. Now, if you use this, it's based just on a number of runs, so it's fully non-intrusive. You first generate your data. You don't even have to make a connection between the software, like finite element software, and then the program that generates the surrogate, because it's purely data-driven. The only challenge somehow is that as you introduce here theoretically an approximation, you need to make sure that this approximation is very small enough for your purpose. So that's what we call validation of the surrogate model. All in all, when you use now this surrogate for uncertainty quantification compared to Monte Carlo simulation, and even more for reliability analysis, you can expect 2 to 3 or more orders of magnitude less runs in total compared to a brute force Monte Carlo simulation. So there are many surrogate models, but for reliability analysis, the one that is probably the most used is what we call Krigging, or Gaussian process modeling. So here I just want to give a few equations. I will not explain all the details, but the idea is that this function y equal m of x, our finite element code, here we replace by this fancy expression where we have the so-called trend here, which is a linear combination of predefined functions, typically just think about the linear combinations of the input variable or polynomial functions. And then this part here is the Gaussian process, which is a zero mean unit variance, and for which we select a certain autocorrelation structure. Okay, so this means that in each point now, that is when I will replace my true model by the surrogate for a particular value of the input parameter x, what I represent here is not just a one value, but it's a Gaussian random variable. So how do we now use the information collected in the experimental design to fit the Gaussian process? As I said, for a new point where I want to predict, so x0 is certain point in my input space which does not belong to the experimental design. In that point, y will be a Gaussian random variable. And what I do in practice is that I will define it as the conditional Gaussian random variable in point y0, knowing that in the point x1 to xn, I know the value of this Gaussian process, because these are exactly the values that I got from my computer code. So there is some kind of statistical machinery behind to then solve this problem, but in the end, we get very simple, quite simple equations. So as I said, for a new point x0, when I want to do prediction, I will have an analytical function for this prediction for the surrogate model. So that's what we call the mean predictor. But the key feature of Krigging is that we also have a local uncertainty in this prediction by the surrogate model. Because we are in this world of Gaussian processes, we also get this local so-called Krigging variance, which tells us, okay, for this x0, the value of the approximate value of the model is this here, but we can also define the variance, and then from this variance confidence interval. So maybe here, just a simple example with a graphical representation. Suppose that my true model depends on a single variable x, and this is this fancy function here, the blue curve. And I evaluated, in fact, this model only at 6 different points here. This is the only information I have, the x and y's for the yellow points. What I get in the end is a mean curve, which is the dashed line here. You see that in certain areas, very close to the true model, underlying model. And on top of this, I get these confidence intervals, which give the uncertainties. So there is no uncertainty at the points that I've used to fit the surrogate. This is interpolating here. And if I take an x, which is far away from all the other x's I had, all the other yellow points, then there is a lot of uncertainty. But the nice thing is that with this Krigging variance, then we can get into some adaptive procedures. So as I know here, the uncertainty for each x, this is the width of these blue bands, if you want. It tells me also where I could put a new point and then run an additional run of the true original finite element model to decrease the overall uncertainty. So this is the kind of process that we can do iteratively. I hope Zoom manage also the videos here. So you see that after a few iterations, now in total, maybe I have 15 points and I have a perfect curve, which is predictive just with these 15 points. This is a general purpose approach, but now we will particularly use it for solving this so-called reliability problem, so computing probabilities of failure. And here, very intuitively, this is not more complex than what's written here on this slide. We start with a very small experimental design, as I said, covering the input space typically, and we will get a first Krigging model, very probably not accurate. But then we will iterate the following. So with the current Krigging surrogate, we will compute the probability of failure, that is replace the true limit state by the current surrogate. And then here, as it's a surrogate model, we can use a brute force Monte Carlo simulation or another simulation method, but with many runs, because the surrogate takes nothing to evaluate. Then we check if we are happy, if we have observed certain convergence, and if it's not the case, we will find new points that are relevant to improve the quality of the estimation of the probability of failure. So here, as opposed to what I've shown in the 1D example, this enrichment criterion will be specifically designed so that the new points give new information or give a better Krigging surrogate of the limit state function in the area where it makes sense to better evaluate PF. So this general idea of active learning, there are 2 seminal papers, one called EGRA, and the other one is actually from the team in Clermont-Ferrand from about 10 years ago with Nicolas Guetton and Maurice Lemaire. And this is the most cited paper in this area nowadays. So it's a very important contribution that has started a lot of follow-ups. Just to show you here quickly how it works. So this is a not so interesting problem. It's just 2-dimensional, just to graphically represent the thing. So the limit state surface here will be here, the minimum of 4 function, which gives certain nice 4 branch in the problem. And the failure domain is outside this area, and we want to compute the probability of failure. So on this slide here, you will see how this process works. We start with the very small number of points here. In each iteration, you will see here at the bottom left, you will see the current estimation of the probability of failure. And the bottom right, you see the current estimation of the limit state surface. So you see at the beginning, it's very wrong. The true surface is the dashed line, and the Krigging based estimation is the black line here, which is completely off. On top here, you will see that at each iteration, we have this so-called enrichment criterion. So we can decide out of many points, which one is the best one to improve the quality. And then if we let this run, you will see that the points that are selected by this so-called active learning, they are actually all around the true limit state surface. So they are automatically found as being relevant when they are here around the true limit state surface. And after a number of iterations, here the first different branches of this system reliability have been discovered, so that suddenly you have a very clear and constant estimate of the probability of failure, and the algorithm may stop. So that's up to now is not really new. I thought it was interesting to, well, just give an overview for those of you who are not so familiar with this Krigging and active learning techniques. Now, the point of this presentation today is that based on this AK-MCS first approach in the last 10 years, there are numerous contributions in this field that claim certain improvement or certain additions to the method. So if you look in the literature, you will find maybe 50 or more, probably more papers claiming a new AK something method. And the point is that, of course, each paper presents nicely what they do, and then they have 2 simple examples where they claim it's a bit better than what has been done before, and that's it. So there was really no way to compare if there are really new algorithms or new ingredients that are very useful and efficient, or if people basically repeat and just vary just a bit certain ingredients and stop it. So we analyzed the literature here. This is a word cloud from all the papers that has been studied. By the way, this is a joint study that is being done by my colleague Maliki Mustafa and Stefano Marelli here in my group at ETH. And so we realized that, in fact, all these active learning methods, they have basically four ingredients. You need a surrogate model, mostly Krigging, but not only. You need a learning function, so there are different possibilities. You need, of course, in each iteration to evaluate the current probability of failure. So it could be Monte Carlo simulation or other algorithm, and you need to stop at some point. So this is a table with probably not a full set of papers claiming active learning methods, but a good number of them, where you see here each line corresponds to a particular surrogate models that has been used, and each column the particular simulation method that has been used. So most of it is related to, as you see here, using Krigging and some kind of Monte Carlo simulation. But there are other options, and you see there are also some empty boxes here. So there could be a possibility to I don't know, to have a supposedly very original contribution using polynomial chaos expansion and important sampling. Why not? But of course, does not really make sense to claim it's something new, because it's always the same story. So we propose to consider that there is basically a general framework here where you can choose independently your four ingredients. It's like a pizza if you want. You can choose your surrogate model, the one that you know may be better, or you know would be interesting and accurate for your problem based on prior knowledge. You could choose your reliability estimation method. There are different learning functions, different stopping algorithms. Here, I will not give the equations for these various learning functions. So they basically built on the current values of the Krigging model. About stopping criterion, there are basically two categories. because of the Gaussian nature of the process. When you get an estimate of the probability of failure or beta here, the corresponding reliability index, you also get bounds on this because of this Krigging variance that we have mentioned already. So you can stop when the bounds are very close to each other. That's one way to stop the algorithms. Or you can just look the evolution after iteration of either the probability of failure or the reliability index. And when it's completely flat after a number of iterations, you can decide that you stop. You can also combine the two approaches. So this leads to this algorithm that I have already commented. In fact, so you start with an experimental design and then you loop by training or retraining the Krigging or whatever surrogate with the current data, compute the probability of failure and some bounds. And if you're not happy with the result, you do for the next iteration, you add a point in the experimental design based on your selected learning function. You update your surrogate and you go one step further. So that is nice. So we realized that, okay, we can represent most of these methods really with the common framework. But the main point is also to know, is there anything that is better than others? So is there any combination of these four ingredients that somehow is better than others? And the only way to do this is to do a big benchmark. So we selected different surrogates here, Krigging and polynomial chaos expansion, a combination of the two, which is called PC Krigging. We selected the two most common learning function. We selected different stopping criteria, different methods to evaluate the reliability in each of the loops, and combine all these possibilities. So this is not exhaustive, but still it's already 41 different strategies of solving this active learning problem. And by the way, this is the reference of the paper. So if you want all details, you can look at this. These are the options for the different models and simulation methods. So here we use what is mostly used, usual ordinary Krigging. We use sparse polynomial chaos expansion. The only thing which is not very usual here is that when we use subset simulation, we call this an overkill use of subset simulation. So we use really a large number of points and these intermediate probabilities, just because once we have the surrogate, the subset simulation costs nothing. So there is no reason not to really hammer this method to be very accurate and in a way to have the exact result for the probability of failure for the current surrogate, so that you don't introduce additional error because of the simulation method. Then we selected 20 different problems, reliability problems from the literature, component reliability, system reliability, and half of them actually that was very easy because there has been a similar benchmark carried out 2 years ago, or proposed 2 years ago by our colleagues in TNO in the Netherlands, which I will also talk about in a minute. So we took 10 of those problems here and others that we got in the literature. The idea here is that we have 20 problems in total that really covers different dimensionality from very simple 2-3 input variables to up to 100 variables, and also very different levels of safety. So probabilities of failure or beta reliability indices from, let's say, 2 to 5, in order to really cover what you encounter in practice in real industrial problems. So 41 strategies, 20 problems. Because all this is based on some kind of random sampling, we repeated all analysis 15 times, which leads to about 12,000 reliability analysis. So that kept our cluster busy for a few weeks. And the idea is now, out of all this big data set, out of all these analyses, can we get some kind of information about what are the methods or combination and strategies that work better than others? There are 3 ways to evaluate if a method is good. First of all, well, you want to be accurate. So for all problems, we have a reference value. We want that we are this epsilon here is small enough. But we also want to apply this later on to a real costly problem. So we want really to minimize the number of finite element model evaluations. And so these are two ways to, well, rank the different strategies. We combine the two in a so-called efficiency factor. As you see, it's just the product of the two. So this efficiency will be really good if both the accuracy is good, small, and the number of model evaluation is small. So that's just an ad hoc criterion to put together the two interesting elements. And as I said, we will then rank the strategies. That is, a particular strategy here is applied to 20 problems, 15 replications, so 300 times. And for that particular problem, we can say, according to one of these criterion, what is the best, the second best, and so on, and the worst one, which is the 31st one. This allows then to rank all these strategies, and this is really over all problems and over all replications, and all problems, as you saw, span a large number of input dimensions from 2 to 100, and also very different obtained reliability indices. So here is the ranking about the accuracy of the final accuracy. And well, there is a very clear thing in the top of the list here. You see that this Krigging or PC Krigging plus subset simulation always comes on top. Then we can also do the same ranking with respect to the smallest number of model runs. Again, here, for instance, the one that is really the best out of 300, out of 41 strategy most of the time is one using a PC expansion with a subset simulation. But if you look also, not just when it's the best, because of course, all those methods, they are not so far away. Most of them are very good. So the comparison about the third digit, what is exactly the best, does not really make sense. So that's why we also put here, is it the best in the terms of most efficient, but also how many times is it efficient within a factor 2 of the overall best method for that particular problem. And you see that with this, typically, the first line here, PC Krigging, subset simulation, and whatever other options, in 80% of all the problems that has been solved, they are the best one, or within 2 times the least expensive method to use. We can do this for the efficiency also. That's another way of ranking. We can then look by method out of all the simulation. Is there a method that is the best one most of the time, or is there a simulation method that is the best one most of the time? So of course there is no single answer, but still there are some message that we can take from these plots here. For instance, out of all the analysis, almost 50% of the time, the best strategy for solve a particular problem involves this PC Krigging. Also, about 50% of the time, or even more, it's used this U function, which is the learning function proposed in the original AKMCS. So there are many more results in the paper. We finally made a kind of wrap up of all these results, which allows also to, because of the detailed analysis of the results, not just globally, but according to the dimensionality of the problem or to the magnitude of the reliability index for a particular problem. This allowed us to give some kind of recommendation. So if you have a problem with smaller dimensionality, and if you expect a very small or very large reliability index, then you have here, let's say, the default configuration that you could use to be very efficient. To conclude, I'd like to, I think it's close to finish. I'd like to also mention that all this was at the beginning inspired by this benchmark, black box benchmark organized by the TNO colleagues in the Netherlands. This was a truly black box benchmark in the sense that they had put together a server with the evaluation of the limit state function, and each participant actually could send a request to the server to evaluate the limit state through their algorithm, and the server will send back the value of G, but also count how many times you call the server. So this way, independently, TNO could benchmark the number of times the method requires, the number of runs are required by a particular method from a particular participant of this benchmark, and what is the result. And they summarize for each of the problem the results this way. So you have here beta in the second coordinate here. The black line is the solution, so the reference beta. And each participant here has one or several dots. So our color is this orange one here, which the dot is how many simulation runs of your limit state did you need to solve the problem, and what is your result, which should be, of course, the best result should be on the line, and the most efficient method should be to the left for this kind of plots. This is the now overall results. There were in total 27 problems, 16 component reliability and 11 system reliability. And our strategy that we devised out of our internal benchmark, you can see here in almost all cases, but 2 or 3, is well, okay, efficient, both efficient and very accurate. So we were very satisfied that this is basically established by an independent external benchmark. So I think I've been a bit long already. So the take-home message is that there is no reason nowadays not to use surrogate model and active learning techniques to solve reliability problems, because, as I said, you get really accurate result, whatever the dimensionality, with a few dozens to maximum a few hundreds of runs of your original model, and this has nothing to do with whatever Monte Carlo simulation technique. Just to conclude, all these techniques are available in our software UQLab. So you may have heard about this. This is a software we developed for a few years now at ETH. We have close to 4,000 users all over the world from 92 countries. And two new or recent news. First of all, very soon, beginning of next year, the next version of UQLab will be completely open source, so free of access to anybody from academia to industry as well. So far, it was free only for academia. And second interesting news is that now there is the identical software available as through a Python-based platform. This is called uCloud. So if you're not a fan of MATLAB, but you want to do uncertainty quantification with Python tools, now you can test it. It's open for now already a few weeks, for a few months for beta testing. And with this, I thank you very much for your attention.